Hello everyone. Today we will study the sound field law of ultrasonic longitudinal waves. It includes 2 points. First, the characteristic parameters of the ultrasonic field. Second, longitudinal wave sound field. The teaching objectives of this section are: 1. Master the meaning of the 3 characteristic parameters of the ultrasonic field and the method of decibel measurement. Second, the master characteristic of longitudinal wave of our ultrasonic field and its application in practical operation. Let's talk about the first point, the characteristic parameters of the ultrasonic field. The ultrasonic field refers to the space filled with the ultrasonic waves. The parameters that describe its characteristics are sound pressure P, sound impedance ZA, and sound intensity I. Sound pressure during the propagation of ultrasonic waves, the pressure applied by ultrasonic waves to the particles, is called the sound pressure of the particle, which is represented by the capital letter P. For plane cosine wave, according to its wave equation, its sound pressure can be divided as capital A is equal to minus rho C capital A omega sine omega open parenthesis T minus X slash C close parenthesis is equal to minus capital P M sine omega open parenthesis T minus X slash C close parenthesis. In the formula, rho is the density of the medium, C is the velocity of the ultrasonic wave, A is the amplitude of the particle, omega is the angular frequency or an angular velocity, which is equal to 2 pi f. X is the distance from the particle to the wave source. From this expression, it can be seen that the sound pressure changes periodically. Usually, in the following study, the sound pressure we often say mainly refers to its amplitude, that is, rho C omega A. During ultrasonic inspection, when the defect reflects back and the ultrasonic signal, the sound pressure is felt by the probe. 2. Acoustic impedance. Acoustic impedance refers to the ratio of the sound pressure P at the point in the ultrasound field to the vibration velocity V of the particle at that point, and is represented by the symbol ZA. For plane cosine wave, its acoustic impedance is ZA is equal to P slash V is equals to rho CA omega slash V is equal to rho C. From the expression of the acoustic impedance, it can be seen that the acoustic impedance reflects the resistance of the medium particle to its own vibration. It should be noted that the acoustic impedance does not mean that the medium hinders the ability of the ultrasonic wave to pass. 3. Sound intensity. Sound intensity refers to the strength of sound wave energy. Generally, sound intensity is defined as the energy of sound wave passing vertically through unit time and unit area, which is represented by the symbol I. For the plane cosine wave, its sound intensity is I is equals to 1/2 rho Ca square omega square is equals to the square of the sound pressure divided by 2 times the acoustic impedance. It can be seen from the expression of sound intensity that the sound intensity is proportional to the square of the particle amplitude and the square of the sound pressure. How do we measure sound intensity? Similar to other physical dimensions, the measurement benchmark needs to be defined first. It is stipulated in acoustics that the benchmark of sound intensity is I0 is equal to 10 superscript minus 12 watt/m superscript 2. And the specified sound intensity level is L is equal to IG I/I0, and the unit is bell, or L is equal to 10 LGL/L0, and the unit is decibel. Simple derivation can get the sound pressure level. L is equal to 20 Ig capital letter P/capital P0, and the unit is also decibel. Here P0 is called the reference sound pressure. For ultrasonic instruments with good vertical linearity, the sound pressure is proportional to the echo height H on the display screen of the ultrasonic detector. So the sound pressure level is also equal to L is equal to 20 Ig capital H/capital H0. With the characteristic parameters of the sound field, let's study the characteristic of the longitudinal wave of our ultrasonic field. In order to fully understand the characteristics of the longitudinal wave sound field, we will discuss the center line cross-section of a beam of ultrasonic waves and the spread of the entire sound field. When the actual wafer vibrates, its amplitude and frequency change gradually from the center to the edge of the wafer, rather than a single amplitude and frequency. Therefore, when discussing the sound field radiated by the chip, we can use the idea of calculus to analyze. First, we discuss the law of sound pressure distribution on the center line. Then takes the circular wave source as an example as shown in the figure. Assume that the sound pressure when the ultrasonic wave radiated by the small area ds of the wafer reaches the Q point on the center line is dP. The sound pressure which the ultrasonic wave radiated by the whole chip reaches the Q point is the integral of countless ds. After integration, we can get the Q point sound pressure. From the integrated expression, it can be seen that the sound pressure at the Q point also changes periodically, and only the sound pressure amplitude is discussed below. In the formula, P0 is the initial sound pressure of the wave source, that is, the sound pressure wave when the ultrasonic wave is just launched, and R0 is the radius of the wave sonic source. In order to make sense here, we make a graph of amplitude function as the figure shows. From the characteristic of the image display, the ultrasonic field can be divided into two sections. The first segment from the wave source to the last maximum sound pressure point is called the near field region, and its length is n. Obviously, the second field in the near field area is characterized by the existence of multiple sound pressure extremes, which is more complicated. After theoretical calculation, the length of the near field area is n is equals to the square difference between the diameter of the wave source and the wavelength divided by 4 times the wavelength, which is approximately equal to F0 is the area of the wave source, divided by 10 times bar of the wavelength. In the formula, FO is the area of the wave source. Simply transfer this formula to get the length of the near field region n times the wave speed c is equals to the area of the wave source multiplied by the ultrasonic frequency and then divided by pi. It can be seen that when the wave source is determined, nxc is a constant. When the sound transmission medium is changed, the length of the near field region changes accordingly. During ultrasonic testing, sometimes two media such as water and steel exist simultaneously in the near field. After a simple derivation, it can be obtained that the near field region in the second medium is the length n2 of the near field region when only the second medium is present minus the thickness L of the first medium, which is converted to the thickness L of the second medium multiplied by C1/C2. Outside the near field area is called the far field area. The sound pressure in the far field area decreases exponentially, which is relatively simple. Especially when the distance from the wave source is greater than 3n, the sound pressure amplitude expression can be approximately equal to Pm is equal to initial sound pressure P0 times the wave source area F0 divided by the product of the wavelength and the distance. During ultrasonic testing, if the defect is located in the near field area, it may be the extreme point of 0 point of sound pressure due to its specific location. The sound pressure of the reflected echo is also different, which can easily lead to misjudgment of defect qualification. For example, a small defect is located at the maximum value of the sound pressure, and another large defect is located at the 0 point of the sound pressure. Obviously, the sound pressure of the reflected echo from the small defect is greater than that of the large defect. Therefore, the near-field region is disadvantageous for ultrasonic inspection. So, how can we avoid or reduce this effect? Please think over. Is it possible to detect from the opposite direction? This is one of the reasons why we require inspection from multiple directions when performing ultrasonic inspection. However, what if the workpiece is small in size and the entire workpiece is located in the near-field region? At this time, we can consider reducing the length of the near-field region. According to the previous expression of the length of the near-field region, it is feasible to reduce the wave source and increase the wavelength. It should be noted that increasing the wavelength will inevitably reduce the sensitivity of ultrasonic detection. Therefore, we should analyze specific problems in detail, and everything should be divided into two, comprehensively considering various aspects of things. In addition, we can also move a part of the near-field region to another medium. That is, have the near-field region in two mediums, and so on. In further study in the future, other measures can also be taken to improve the detection accuracy. Well, that's it for the second sound pressure law on the center line of the ultrasonic beam. Next, we explain the sound pressure distribution on the cross-section as shown in the figure. It can be seen from the figure that on different cross-section there are multiple sound pressure extremes, points for the sound pressure in both the near field and the far field regions. But they are also different, mainly in 2 points. 1. The number of sound pressure extreme points in the near field area is more than that in the far field area. 2. The sound pressure at the center point in the near field area may be the real 0 point, while the center point in the far field area must be the maximum value and the maximum value. Therefore, in the future, ultrasonic inspection, it is necessary to use the far field area as much as possible and make the center of the sound beam vertically aligned with the defect. Otherwise, the accuracy of defect location will also be reduced. And now, let's talk about the diffusion of the ultrasonic beam, that is, the directivity. In the previous study, we know that the actual ultrasonic wave is similar to the plane wave when it is closer to the wave source. In theory, the plane wave is non-diffusion. When the distance is farther, the ultrasonic field begins to spread. Therefore, from the point of view of diffusion, the sound beam can also be divided into 2 sections, namely the non-diffusion area and the diffusion area. After periodically calculation, the non-diffusion length B is equal to 1.64 m. The diffusion in the diffusion zone is shown in the figure. The abscissa dc in the figure is the directivity coefficient, which is equal to the ratio of the sound pressure at any point in the sound field to the sound pressure at the center point of the same cross-section. The ordinate y is equal to kr0 sine theta 0, k is the wave number, equals to 2 pi / wavelength. When y is more than 3.83, that is, zeta is more than theta 0, dc is less than 15%. This shows that the sound pressure outside zeta 0 is very low, and the energy of the ultrasonic waves is mainly concentrated in the degree of 2 zeta 0. Therefore, zeta 0 when y is equal to 3.83 is often taken at the age limit of the sound beam, and zeta 0 is called the half diffusion angle or pointing angle of the sound beam, also called the first zero value divergence angle. After periodical calculation, zeta 0 is approximately 270 lambda / d0. To sum up, the longitudinal wave sound field radiated by the disk sound source should be shaped as shown in the figure. Well, that's all for today. Thanks for your watching.